Videotaping class for people who are at our mall. Everyone else, I feel like I need to collect a couple of homeworks from this week. Wait, when was this homework due? The one that they're doing right now?
Wednesday.
Yesterday? Oh, it was just yesterday, right? No, 2 days ago.
Yesterday.
Wow. I'm so confused.
The day before yesterday.
It was due on Wednesday? And then there was more homework due yesterday?
Yeah, you collected the homework yesterday. Yeah.
Oh, I did?
Yeah.
You collected the homework due yesterday.
No, I'm just
You
so...
collected the homework due yesterday. You did not collect the homework due Wednesday. There was no homework due today.
Okay, perfect. So I need to collect... So I think I just need to collect the homework due Wednesday, so can you take it out? There were two... I don't know exactly, because they're clearly not totally up on what's going on.
Page 398 and page 408.
So, there were two problems, both on constructing tangent lines to conics, both of which were, oh yeah, this is slowly coming back to me now. Yesterday was all the polar stuff. So it was page 409, and basically there was one easy problem, number 10, which was, here's a parabola, it's the simplest parabola possible, y equals x squared, and we would like to know the equation of the tangent line to this parabola. It appears that Lawrence has just done this problem, probably correctly. What does he do? He says, no picture required, because... Yeah, what he says, that's a joke. Picture's always required. So here is the parabola, and what we are looking for is the equation of the tangent line to the parabola. And what we know about this tangent line is it has coordinates 3, 9, and what we don't know is the slope. So he writes the general equation of the line, it's got to be in the form y minus 9 equals mx minus 3. All we don't know is m. And so he says, well, the tangent line is going to be the line such that it intersects the parabola at exactly one point. So he moves the 9 over. This is the tangent line, of course, still containing the parameter m, which we don't know. And he sets the equation of the tangent line equal to the equation of the parabola. And this is now my equation. When that equation has no solution, when exactly one solution, then that's the correct m. So he rearranges it in a kind of standard form, and this is an x equation. This is an equation solving for x. And when this equation has one solution, that is the correct m. This equation will have one solution when b squared minus 4ac is 0. So we get this, and then we solve, and it happens when m is 6. So therefore, the equation of the tangent line is y minus 9 equals 6x minus 3. Are we good? Okay, that was the easy one. Then the hard one. The hard one was finding the equation of the tangent line in general to an ellipse. I'll provide a picture. And can you peek in the camera can you recenter on what's going on? Don't zoom, just like turn the camera possibly. So the equation was 9x squared minus 5y squared equals 44, which is pretty disgusting actually. I don't even want to graph that, do I have to?
Wasn't it
I guess it.
44?
Oh, it's because it's a hyperbola. That makes it even worse. I hate hyperbolas. So this is going to be x squared over 44 ninths. Right? No. Yes. Yeah. Minus y squared over 44 fifths.
No, it's y squared first. Yeah, it's y squared first because it's negative 44 and then you divide.
Wait, am I right or wrong?
You're wrong. Wrong. It's
Why am I wrong?
because when you put the 44 on the other side and then when you divide.
Oh yeah, negative. And then you
Like,
have
when
y.
you put
X
the
is
44 on the other
negative
side.
because
Negative
negative 44 is
So when you divide through the x term becomes
and
negative.
it's not 0.
Because 44
Okay. Finally, I understand what you guys are talking about. Perhaps I'm too slow. So what you're actually saying is that this is 5y squared minus 9x squared equals 44.
Negative. Yeah.
Therefore, it's y squared over 44 fifths minus x squared over 44 ninths equals 1. So what the hell kind of hyperbola is this? 44 fifths is like about 9-ish. So this is going to be about equal to 3 squared, and 44 ninths is about 5. Oh, this is kind of not so bad. It's about 5. So this is going to be about 2.2-ish or something, 2.5-ish. Right? Yeah. Squared. Alright, so what does this hyperbola look like? This hyperbola is going to be vertical. It's going to have a thing at roughly 3 and ish, and it's going to have a happy box of roughly 2.5. So, making the thingies, we now have pretty much this hyperbola is going on. Alright, and what are we supposed to do? We're supposed to find the equation of the tangent hyperbola at 3, 5. Well, that does seem reasonable that, according to our picture, that the tangent line will go through this thing at 3, 5. And what does that tangent line look like? Something like this. Okay, how do we do it? Well, he says, just like before, he says, all right, the equation of this tangent line is y minus 5 equals mx minus 3. I need to figure out what m is, and he just basically does a nightmare of algebra here, which is impressively executed. So this is the equation of the thing. This is the equation of the tangent line. Now you can't quite set them equal to each other anymore because they're not the same. So what do? You just solve for, he just takes this entire y equals line and substitutes it in for y in the equation of the hyperbola. And then just grinds out a massive algebra explosion. And eventually factoring it all out in a standard form for solving an x equals equation. And it is a quadratic, or it's a quadratic in x. And I would like to know when this quadratic equation in x has exactly one solution. Well, that's going to happen when b squared minus 4ac for that equation is 0. So then he makes a new equation involving m's, and it is like a quartic in m's, but the quarticness of it kind of cancels out. And after much algebra, factoring, dividing, etc., we find that the slope is 27/25. Yes?
Is it okay if we leave it in point slope form, or do you want us to?
Oh yeah, that's perfect, just like that.
Okay,
Yep.
sure.
Raise your hand if you got that, 27/25. It's like pretty hard. Oh no, wow. Okay. Cool. There were a couple other problems from this homework. Do you want to do like 1 or 2 of them quickly before I collect it?
Is the tangent line going to be on the test?
Yeah. I think I put the objectives up last night for what's going to be on the test.
Yeah.
Do you want to go over? I think I assigned yet more problems from page 398. Is that correct?
Yeah, can you do number 39?
Which one?
39.
39. We sure can. 39 says, can you turn the camera so that you can see what's going on over here? 39 says that it is conic, and the center is at 1, 2, and the directrix is x equals 7, and the corresponding focus is at 3, 2. And it says find the equation of the conic. Okay, there are a bunch of ways to do this. All right, let's draw a picture. So we draw a picture. The center is at 1, 2. The focus is at 3, 2. So that's 3, 2, that's 1, 2, that's the focus, that's the center. And then the directrix is at x equals 7, so 4, 5, 6, 7. Okay. Well, so, what should we do? Well, the distance from the center, so I guess I don't even know what this is yet, right? Do I? I guess I don't. Oh, okay, so here's what we can do. We can take, alright, so this is 2, so C has to be 2, right? Do I know what kind of conic this is yet? It's going to be, why do I know it's an ellipse?
Because you're a D. D is 6.
Oh yeah, okay, so we can find D. D is just going to be 6. So D is 6. And then just like use the equations and stuff pretty much? Yeah, okay. So one of the equations, what equations involve C and D?
D equals A squared over C.
Yeah, alright, so it's like more work than I thought. Okay, so yeah, so if D is A squared over C and C is 2, okay, that's not so bad. So D is 6, so I get 6 equals A squared over 2. So that means that A squared is 12, so A is 2 root 3. And if A is 2 root 3 and C is 2, then the eccentricity is 1 over root 3. Because eccentricity is C over A. And since that's less than 1, it has to be an ellipse. Seems like a roundabout way of doing this problem. But whatever. And then you can just kind of take it from there. I don't know, is that good enough? The other thing you could do, by the way, there's no shame in just doing the whole thing out based on the definition. So that's also like another possibility. If you tell me where the focus and directrix are, isn't that just like enough? Oh no, it's not, because I don't know the eccentricity. Yeah, so you kind of have to do this. You do have to do this. So once I know that the eccentricity is 1 over root 3, I know what A is, I know what C is, I know now that it's going to be what's A again? 2 root 3. So that's like 3.4-ish or something like that. So it's going to be some kind of a thing like that. Now I guess I just need to figure out what B is. Well, in an ellipse, B squared plus C squared equals A squared. So if A squared is 12 and C squared is 4 and B squared is 8, so B is 2 root 2. So this is going to be, and it's going to be horizontal, so this is going to be x minus 1 squared plus y minus 2 squared equals 1, and the A has been stretched out by, this is going to be 12 and this is going to be 8. Is that what you guys got?
Yeah.
Okay, cool. Okay, cool. Yes?
I'm just going to comment that I think you could tell it's kind of an ellipse anyway from the graph. It's not a parabola because B isn't equal to C. And in a hyperbola, the directrix would be between the center and the focus. So.
That's true. Yeah. Good. Okay, can I have this homework? Let's put it right here in the center table. And now we're going to do something that's really, really awesome. Yeah, I did. That was all in one day's homework, right?
Should we also put in rotated products?
Realize space.
Hold on to that. I'm going to collect that next week, I think.
Swipe.
Alright.
I was being lazy with it, and I
Can you give everybody one of these?
Of course I did.
Alright. So, we're kind of done. What we're learning today is not really a new thing. Can you and turn it and like move it back like 5 feet or so we can get like most of the board. So, what we're doing right now is not really a new thing. It's just kind of an awesome understanding of something that we've already been doing. You okay with this? Seem a little unsure, but loosening things and tightening things. Wait, let go. This, tightening this, stops the up down.
Yeah.
Whoa.
But I want to like loosen up.
Okay, hold on. Man. Okay, this needs to go up. This should be tight. This should be like that, and then tighten it, and then, yeah, that should be good. Are we good? Okay. So, check it out. Here's a problem I gave you. Oh, here we go. So recall, notice that supposedly we've been doing conics and polar, but did you notice a distinct lack of actual any polar anything happening?
Yeah.
Yes, so now let's actually do that. So let's recall what r equals 3 plus 3 cosine theta looks like. Please take a moment and graph that using whatever means are at your disposal. probably like the way I taught you seems like a good way. And I will waste the time of my life tediously drawing circles because you've let me down.
Oh, it's okay, baby.
All right.
So it's a carrot to why are you playing?
Don't guess, man. What are you supposed to do? Josh Rewan, what are you supposed to do? This is like a nice review for the final exam in graph 2. Everybody else, what are you supposed to do if you want to graph this Limacon?
Well, grab some points and you know, like,
Not really. You make an auxiliary graph. Remember all this?
Oh, really?
So I want to know what this looks like. I make an auxiliary graph, y equals 3 plus 3 cosine x. And that auxiliary graph is going to be just a simple thing like so. And pi over 2, pi, 3 pi over 2, and 2 pi. And it's just a cosine curve moved up 3. So it's going to look like this. And I use my auxiliary graph to help me, yeah?
Sure.
Sure. Yeah, so the auxiliary graph tells me that when theta equals 0, r will be 6, which means that I start out here at the point 6, 0. And when theta equals pi over 2, r is 3. So I'm over here, and then when then I'm here, and then and then I'm here. And it also tells me what's happening over the interval from 0 to pi. What's happening over the interval from 0 to pi is that my r value is steadily getting smaller. So you should make your r such that it's steadily getting smaller. And then when y is 0, that means r is 0, which means we touch the pole. And now r gets steadily bigger over the interval from pi to 2 pi. Okay, this is all review. Are we good? I'll even include kind of like arrows so we sort of see like this is the order in which this curve is traced out. Okay, well, now suppose way back in February when we were doing polar, suppose I had just given you out of the blue r equals 1 over 3 plus 3 cosine theta and asked you to graph it. Oh, Alex Ma, what do we know now about 1 over 3 plus 3 cosine theta? It's a conic. What kind of conic is it? It is a parabola. Now we know to treat this as r equals, well, I divide the top and bottom by 3, so it's like 1/3, 1 plus cosine theta. Ah, ha, 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 ha. That is going to be a conic. Specifically, it's going to be a conic with eccentricity 1, so it is going to be a parabola. But supposing you didn't know that, and supposing you were just forced, like Fried's Nefroid or whatever the hell, to try to graph this, how would you go about doing this? Possibly. Yes, Amy.
auxiliary graph.
Correct! How did you know that that was the correct answer? Yes, we will make an auxiliary graph. So we will simply make an auxiliary graph for the equation y equals 1 over 3 plus 3 cosine x. And then we will use that auxiliary graph to help us draw the graph of this thing, right? Okay, so everybody use your skills in reciprocating curves to reciprocate this sinusoid and produce the auxiliary graph. What's it going to look like? Someone say something smart.
You have an asymptote at pi.
Yes, asymptote at x equals pi. Because when, x is 0, so like, let's just pretty much just like do it, right? At 0, what's the value going to be?
It's
1/6 at pi over 2, what's the value going to be? Yeah, 1/3. And then as I approach pi, the cosine curve is going to give me a tiny positive, so the reciprocal is going to give me a huge positive. So we get, and then it's like totally symmetric, right? Is that right? Yeah. Now we can use this. Auxiliary graph to help us graph this thing that I now know to be a parabola. All right, let's start. Where am I at when theta equals 0? 1/6. Whoa.
Do we want to cheat here?
It's too late. So this point is going to be like 0, 1, no, 1/6, 0. And then what happens on the interval from 0 to pi over 2? Yeah, but like not freaking much happens, right? That entire interval from 0 to pi over 2, all that's happening is a little, and now I'm at 1/3, pi over 2. Isn't this exciting? I'm like really excited. Now what happens on the interval from pi over 2 to pi? Yeah, sound effects. Have you guys learned nothing all year? Only Amy understands that the only correct answer involves some weird noise making. Yeah, yes. The y, as x gets closer and closer to pi, y goes to infinity. So in other words, as theta approaches pi, r goes to infinity. All right, now, it's unclear exactly how r goes to infinity. It would be tempting to kind of draw it like over here, right? But we've seen several examples last time where it doesn't actually work that way. And the only real way to do it is to convert it or do some kind of partial conversion. Okay, but now since we know this is a parabola, we kind of know that it's just going to do like, so, sort of, yeah. And so this is what happens like when theta equals, like what? Pi over 2 minus. Right? Pi minus. Pi minus. Yeah. Yeah, so this is like some kind of weird like infinity comma pi minus polar point or something like that. And then what happens? What happens next? Suddenly I'm a tiny bit more than pi, and now the auxiliary graph tells me that I'm at a little bit more than pi comma infinity. So that means that if my theta value is a little bit more than pi, I'm going to be like way out here, right? So this makes me way out here. And then what happens over that interval, r gets much, much smaller. By the time I get to 3 pi over 2, I'm back at 1/3. So that's like 1/3 comma 3 pi over 2. And then it looks like this. That's the most terrible parabola I've ever seen. And this is theta equals pi plus. Okay, so that was kind of interesting. That kind of links together what we know about graphing polar curves and what we learned a couple days ago about the fact that this is a parabola. Okay, but Sophia, this is the boring way to do it. What we have just done, think about how lame it is, what we've just done. We had a Limacon. We got the Limacon by consulting the auxiliary curve. And then we got this parabola by consulting its auxiliary curve. But this auxiliary curve is the reciprocal of this one. Why don't we need rectangular graphs at all? What we really need to do is we need to do polar reciprocation. Let's go directly from the cardioid to the parabola. This is a deep thing that we've just learned. What we've essentially just learned is that if you polar reciprocate a cardioid, you get a parabola. Okay, everybody try to do this. Take this cardioid and polar reciprocated. Do you understand what I mean by polar reciprocated? Like, take all the R values and make them the reciprocal of their current R values. So what happens is, if R is big, then it shrinks in. And if R is small, then it explodes out. Do you see it happening? So it's like, okay, it's like I call this an inside out.
Heart attack.
Yeah, it is like a heart attack. That's a good one. Yeah, so the like right ventricle and right atrium are like squeezing in, and they become the like vertex area kind of the cardioid, and then the like whatever that is, the aorta, just explodes into this massive infinite behavior here. Cool? Alright, good. So that's the inside out exploding parabola. Okay, we're just getting started. Page 2. This time a little bit faster now. Make an auxiliary curve for r equals 3 plus 2 cosine theta. Graph that polar curve, and then graph the corresponding edge. Just like do the same thing we all just did. Someone check the camera that it's like still generally focused on the business. Okay, this one's a little bit less fun, right? But it's still pretty fun. So, this r equals 3 plus 2 cosine theta polar curve, I happen to know by making my auxiliary curve, it is going to be a kind of relatively boring Limacon, right? Where when theta is 0, r is 5, and then r gets slowly smaller until here. And then it gets even smaller. And I think this one's going to have like a dimple in it, right?
Yeah.
So I get something like that, right? And now, in order, had somebody back in February or whatever asked us to graph r equals 1 over 3 plus 2 cosine theta, that seems really hard, so we would make an auxiliary graph, which is what we do over here. And this auxiliary graph is not that exciting. When I plug in 0, I get 1/5, right?
Yeah.
Okay, right. Yeah, and when I plug in pi over 2, I get 1/3. And when I plug in pi, I get 1. 1/3. 1/5. And that should help me make the auxiliary curve, or that should help me make the polar graph. When theta is 0, I'm at 1/5. At pi over 2, it's 1/3. At pi, it's 1. And then it just kind of goes a little bit. So what we got is a tiny little cute ellipse. And everything we just did makes total sense, but it is more fun to inside out explode this initial dimpled limacon by polar reciprocating it. And when we polar reciprocate it, it just kind of goes like, and it just like goes in, right? All this 5 becomes a 1/5, and the 1 just stays there. So okay, awesome. Okay, good. Next page. Now we get to the serious business. This was all just warm up for the greatest freaking moment of your life right now.
You said that way?
He said that like a million times.
Every single time I mean it. You just fix it? Yeah. And make a really accurate auxiliary graph, because I want to know like exactly for what theta it crosses the pole, like et cetera, et cetera. You know what I'm saying? And it is the last polar graph I'm ever drawing on the whiteboard in my entire life, right? By next year, I'm going to have my machine.